Well, this is part one of this video. I received this faceplate along with a bunch of other parts about 2 years ago now. And I'm not gonna lie, I've been kind of avoiding this build because I knew it was gonna be a giant time suck. This is a faceplate out of an SP220. And this is, this whole thing is owned by a guy that, Space Age Signs is his business. And he's out of Newport, Florida, Newport Richeyville, Florida. And he came up with this vinyl wrap, which is just sick on the first order, in my opinion. That's really cool. So we're gonna set this aside, and I've been taking very good care of that for about 2 years. Here's the problem. It's not really a problem. These are all things that we're gonna work through. Here's our stock knobs, okay? Here is one of our stock meters. Now, unfortunately, that's one of the lenses for the second meter. And that's our second meter in total. Now, as we can see, this might have been good at one point, but maybe, I'm looking down in there, I see there's some schmoo stuck down in here. This was put loosely into a little bag. Oh, maybe it's still good. Let's give this a quick test. This is put loosely down into a bag, and it's taken a little bit of a beating. That's ground. Oh, dude. Dude, you got lucky. Okay. Let's bring that up to 0. Let's marry this with the faceplate. So, needless to say, I'm going to shoot this on the weekends, and I'm going to work on this in my spare time, because this is like, the meter's falling apart. Let's just stop. Let's just stop. We're we're going to have to paint those. We got to paint the knobs to make everything look right. We've got to do this just in a certain order. I'm stoked that those meters still work. Here is the rest of the miscellaneous bag of parts. It's the backlights for the meters, the knobs for mode control, and here's a selector knob for mode control, which is surprisingly not broken, and the sensitivity select. I don't know how much of that we're going to keep into play, but what he wants me to build him, parts falling out of the flipping bag, what he wants me to build him is really cool. But I look at this and I go, oh God. So this is the case that he sent up, which is in really good shape. This all black case, which is in really, really good shape. A little dusty from sitting up here for so long, but this case is in really good shape. This is our RF deck. This is going to be a 4-tuber when we're done. Stock blocking cap. I don't know what all this capacitance here for the bypass is. We'll work through that. Airflow in, airflow in. Let's take a look at the bottom. This was working. Was. Nuts and hardware falling out of this thing. It's another thing, is the mounting hardware is completely MIA in the back of the meters. Four tuber. Dual plate chokes. Here and here. I mean, in theory this will work, but there's no input tune. RF comes in, goes through the relay, drops right onto the tubes. There's no input tune. So our bias circuit's a little messed up. There's a lot of stuff going on here that I'm going to have to come back and address. But, like, output coax is all melted. This at some point or another was working. Here's the back of this thing. Now, the way that he has this labeled, base filament number 1, base high voltage switch number 2 on and off. So he wants to be able to switch the high voltage on and off, filament on and off, and then operation standby. And then this here for the meters, which that's what we've been supplied for the meters. And then he wants me to remote the shunts from the power supply up to this. Oh, and I got to build the power supply, which I happen to have the transformer for this, and I've been holding on to it for ever and ever and ever and ever and ever and ever and ever. It's a Peter doll that I have. There's a couple things that are wrong here, like this filament transformer. I have to create a shield around this filament. These are the leads that go to the bottom of the tubes, and they're going right by our primary output RF. I have to create a shield around this transformer because there are no horns on this transformer. And so the RF that's getting generated up here in the deck can affect the windings of the filament transformer and cause an oscillation issue. This is going to be time consuming. There is no doubt. Very, 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 very time consuming. But I did the 3-tuber, and I'm not going to lie, I took this on because I wanted to do it. There's a lot of old schoolers out there that are like, whoa, 4-tube. It is possible. I want to do a different plate choke because this one's got a hole in the middle of it. And I want to change where the plate choke sits. I want to change how the high voltage comes into the deck. Like this is all busted up down in here. Let me show you. Here we go. There we go. That's all busted up. The thing's filthy. Gross, but there is potential. Now, someplace there is this plug, and I need it. Because remember, over here, the filament's no big deal. I can control that from here. But the high voltage, on the other hand, I'm going to need a multi-port plug, and there's some other stuff that's going to have to go on to where I can make these meters basically read correctly and read roughly accurate. There's going to be a little bit of communication that goes between the power supply and this. So around here someplace, I have seen this plug. I know it is here. It's just going to take me a while to find it. But like I said, this is just the beginning, so let us begin. I'm not going to lie, I'm a little disappointed in myself. I went back and looked in my video archive, and I shot a whole segment showing how we got to here from what you guys just watched, and It's gone. Like I was saying, I shot a whole segment here showing how we got to this place. I went ahead and got rid of everything in here I didn't like, and we are starting the F over. There was a lot of things in here that I was like, no, and it was really, really, really dirty. So, you know, we start over. So we're gonna have a fan blowing in here, and then we have another one that blows in over here, so it's gonna get like cross ventilation. The downside is there's not gonna be any air on the pins on the bottom. But I'm working with the suspicion that this amplifier was in a working order at some point, right? So somebody put this together and they got it fairly close. So one of the things that we're gonna keep is this here, this little stud. That's our bias flop. So we're going to take our center tap here and we're going to run it here. One of the main things we're going to do is we're going to do away from this, running everything through this hole. You know, we got lots of other holes in this cabinet that we can utilize, and it doesn't have to, like, the anode control wire that controls the tube doesn't need to lay against the final output line that goes to the outside. I'm trying to work out in my mind what I want to do here with the filament chokes. We shouldn't need to have two, but I know that, well, I'm going to reserve on what I know, and I'm going to defer to an expert. So that means this afternoon I'm going to call the man, the myth, the legend, the king of the 3500Z Yellow Jacket. So on that note, let's change some shit. Oh. And I think I mentioned in the last segment, where is it? Here it is. That I could not find this plug. And a customer had sent the plug, but then I had to go out and do a search for this plug because I couldn't find it. I lost it. Myself lost it. It disappeared in shit over here. Shut-a! Look at that. Oh, it's so pretty. So now we've got a communications plug to marry up with the plug that's in the base of this thing. And so from here down, we've got to run all of our metering circuitry through this, our 110 volt, 220 volt, ground, all that kind of stuff has got to come through this plug. So we will start. On that note, let's get with it. Let's go over everything I did today, because this was my day in a short. We started out doing a bunch of wire maintenance, right? Like, a lot of this stuff was just hanging on by a prayer. So I went and I got rid of a lot of things. The only thing that's left, this rubberized wire, is the filament leads. Everything else has now been converted to Teflon. So the bias center diode, I replaced that wire with Teflon. I organized and tied everything in place. Our DC 125 volt lead that runs around here and also runs the relay, it's all been replaced with Teflon. I cleaned up all of this mess, got rid of all the garbage that was on the back of that metal back there. I don't know what that metal was, but that is a piece of repurposed, and metal plate, good to go. Clean that off, call it a day. Checked all the sockets, those are all good. Completely rebuilt this filament attachment, which was cracked and broken. Went ahead and put two new blockers in here, two new disc capacitors to help throw this out of resonance, even though we've got more than adequate over here. And then we went ahead and we wired up the filament. I'll show you that here in just a minute. This here is the pass-through tune on the box, which is not too horrible. And what we're measuring there is the coax, the RF coming in on this coax, coming around, goes around in a loop, then it runs up here to the relay. I had to do the relief loop because it was too tight of a degree angle and it'd be pushing against our choke mount. So I brought it back in a loop. It actually hoops in a loop underneath here and it comes back, goes up, goes through the relay, Then it comes down and passes out of the relay, goes through the 393 and over here to the PL259. I changed out the two PL259s because the one PL259 that was in here on the final stage has seen way better days and was starting to get hot. And there is no way I would trust that stock connector to carry the power that is going to go through this thing. So now it's got brand new PL259 coax connectors on the back to let them love out the back door. Brand new input and output coax. Relays tested, it's working. This whole circuit up here is now working and right. I don't know what people were thinking when they were in here before. So then I went and I laid down the groundwork for the input network, which I'm going to stop on this. We'll come back to this down the road. So when the relay closes, click, the signal that's coming from the input coax then gets switched over to this piece of coax, and the RF comes over, loops around, and goes through this inductor. This is going to be our PIL circuit. So that means we're going to have a capacitor here coupled to ground, and then another capacitor here coupled to ground. But then we'll have another inductor that comes off and goes through the front of the cabinet, and it'll come up to an air tuner that's in the front, which will allow him to specifically dial in his input tune. Okay, sorry, long day, a lot of BS, just a freaking Monday. Oh, I hate Mondays. Let's go ahead and let's get the network analyzer out of the way. The only thing I did on the amp side of the deck today was wire up the filament transformer. So the way they had this wired before was with 12 gauge wire for, like, let's say Romex up here on the top. So the 100 and some amps worth of 5-volt bullshit that's going to come out of this transformer, shmoo, went directly down through this hole, and this is our primary output lead to go to the output of the amp. Well, I didn't like that, so I got, this is high temp silicone boot wire for like RC cars. And the advantage to that is it's got 7 billion little angel hair strands in it. And the jacket on it is designed to put up with about 7 million degrees. The other thing we did is we ran the wires through a grommet. Also replaced the center tap wire with a piece of Teflon and hooked that all into the bias circuit down below. So I'll come back later and I'm going to tie this in. Now, the reason that we got to go with high temp wire is 2 reasons. Let's drop this broken 3500Z in the spot. Okay, let's change the orientation of the cabinet one more time. That glass bottle gets hotter than shit. And it's right next to this transformer. Now this transformer doesn't have a horn on it. And they're called horn caps that fit over the outside of this thing. And it's what keeps the filament transformer from getting saturated from RF from the RF deck. This transformer doesn't have that. So what I've got to do now is I've got to come and build a copper sheet or something made of metal, either aluminum or copper, that's going to sit between the filament transformer and the tube. And then I have to create also yet another shield on this side to block all the RF that's coming from the tuner and the tank coil that's going to be present and all of that stuff, so it can't infiltrate plate transformer and cause this thing to go crazy. You can get yourself worked into a corner with any and all tube amplifiers if your filament transformer's in your RF deck. RF deck's got a bunch of RF floating around in it. Well, the turns in the transformer can absorb some of that energy from the RF deck and in turn feed it back into the tube, which will make your tube go crazy once you start to come up in output power. So we got a little bit more fabrication work to do. That'll be on the top side. And then I've got to build a shield that comes up, and I got to put a lid on it of some kind, and I got to make it so that the lid has air holes because this thing is going to get hot and it's got to be able to breathe. Just the beginning. We're just getting started. This is where I got to stop for the day. This is the end of my day on this for this afternoon. And then next week, we'll start with our switches, our on-off switch, our filament switch, and we get our plate choke, our bypass cap, we get our high voltage wire hooked up over here on the Molex connector. We will get this cage built, the RF shield. We'll get that all mocked up. And I want to get as much done as I can do before I put the faceplate on this thing. The faceplate is a vinyl wrap, which means it is very, very, very susceptible to scratches. Oh, I did one more thing. I want to show you one more thing. So what we did is we color matched the knobs to the cabinet. Taped these off, painted them up. We did the same thing with the meters, taped them off, painted them up. I got to come back and clean the window. But that's now black. These are now black. That's gonna look sick. Now remember guys, I'm not the first one to do this. I know this. There was people building 3500Z boxes long before I was even anything floating around on my dad's nads. Okay? But I'm the one currently doing the project. So I'm gonna do it the best that I can with the parts I was given. And I was given really good parts. So, not saying I'm doing anything special here, because Lord knows I'm not. There's been people doing this a lot longer and a lot better than me out there. So, with a humbled amount of humility, I say, gentlemen, we'll see you here next week. Well, hell. Okay. So here we are. This is our little plate transformer that we're going to use. As you guys can clearly see, this is a 230 volt on the primary, and it's a 3000 volt on the secondary, which will get us right around 4000-ish volts. 4003 float under load. It should drop down to about 3800 volts, which should make these tubes just scream. It's continuous duty, or CCS, 1.5 amps, which should be just right about what we need for 4 tubes. And it should do it wonderfully, I feel. This is an old plate transformer. It's been sitting up underneath my workbench for 7 years. This was in a old 3000 that I had bought way back when from my buddy Butcher Boy. That was my first 3000 I had. I bought it from him as, well, a parts box. And I ended up ripping it all apart, and this is one of the things I replaced immediately because that voltage is way too low. A couple thousand volts too low anyhow. So I set it aside, and I knew that I'd have a project for it in the future. Well, here we are in the future. Now the reason the pan on this thing, I flipped it upside down like this, was for one reason and one reason only. This is our 4500 volt 32 UF electrolytic. Let's zoom on in here again. Make it real easy for you guys to see. Old GE, we bring good things to life. If the pan wasn't flipped over, our filter cap would go up towards the roof. Now we've also got, I don't know why when people scrap things they don't bother to keep certain stuff, like the mounting brackets for the cap. I am thinking, I'll get that moved out of the way again. I'm thinking this is going to be the front. This portion here is going to be the front of the box, the power supply. I am going to put a voltmeter on the front of this thing for safety's sake, and we're going to have a voltmeter up on the RF deck for safety's sake. And I think I'm going to put my 3 switches right down here. You know, your on, your filament, you get it. So, or no, the filament's going to be up on the RF head. That's right. So all we're going to have down here is on and a high voltage switch. We will not have a high-low, so we're just going to have an on and the high voltage switch down here, and then a filament, which will also kick on the fans and everything on the RF deck. It'll be on the RF deck, so. But I got to get this laid out, and then the next thing I got to do is I got to go cut some phenolic, or not phenolic, but some red fiberglass sheet, because I got to build a bleeder bank. And speaking of which, I need to get my 10A10s. Need to build this rectifier board. Bleeder bank, rectifier board, glitch circuit. Here are our contactors for our soft start. Way overkill, way bigger than what we need. But that's cool. That's what we need to do. And somewhere over here on the shelf of misery, this is going to be our Fujitsu. Is it Fujitsu? It's going to be our Fujitsu copy time on timer, which we're going to use for a soft start circuit. So a little bit bigger cabinet than what we needed, but I'd rather have a little bit extra room for a change instead of trying to shoehorn 5 pounds worth of shit into a 2-pound bag. So yeah, let's get with it. It's time to start doing some wiring. Okie dokie here. So I've spent my afternoon working on bleeder bank, rectification diode strings, and my new plate choke. Bleeder bank is easy. That's to get rid of the high voltage in the filter circuit. I've covered this in many YouTube videos, why I build like this. There are guys out there that have way mastered this, and they've got board designs that are way scoochum cool and pretty with green and gold and all kinds of different color masts on them. I like to build them myself. These are 10A10s. There is 10 legs or 10 diodes per string, and the reason we're doing that is because we're wanting to rectify about 5,000 volts roughly. Remember, diodes are cheap. Shipping to get thing back across the United States because one diode went bad, expensive. Each one of these diodes is only a couple cents. In theory, these being 1,000 volt, 10 amp, 10A10s, I could use 1, 2, 3, 4, 5. That right there is enough to rectify, just them 5 diodes, is enough to rectify 5,000 volts supposedly at 10 amps. So I could have this whole string cut down the middle, have AC come in here, AC come in here, ground be here, and positive be here. I'd rather make it so that the diodes are not having a rough life. And what do I mean by that? I'm going to use 10. I double down. So now we've got all kinds of headroom in the parts and we're not running at max saturation. I want to double down again so I can increase my amp load. We're building an amp that's going to suck up approximately 2 amps worth of jizz current. Okay, and the only reason I can get away with that is because that transformer is CCS rated. You know, it's not intermediate at like 30 or 40% duty cycle, it's continuous. So we're going to overtax that transformer just a hair, not a lot, just a hair. But we want to also be able to understand the fact that we need to have heat dissipation. So we double down and we increase our current capability, which means all of these are going to loaf, and then we double that again so we can increase our current. This is, the 10 is for voltage, this 10 is for extra amperage. So now each string is only this 5 and this 5, this 5 and this 5 is only going to see a quarter of the total operation load. And we're only going to see about half of our rated voltage rating. So we've got a lot of redundant headroom built into this board. On the back side, the most time consuming part. Yeah, we took all 100 and, let's see, 40. So here's 10, 20, 40, okay, 80. We took all 80 diodes, had to bend each one of the legs. Then we had to get out and drill the board out, all 160 something holes, right? And then we had to hand twist these all together. The reason we hand twist them and not just do the solder joint, this is what I like about the circuit, and the reason I like to still build my own, is on most of the boards, they're just populated. The diode's bent over, the leg's bent over, and the wire just goes through the board and you solder it to the trace. In certain situations, the diodes can get really hot, and what ends up happening is the heat transfers to the back of the diode legs and they can unsolder themselves. By twisting the legs together, we have a physical mechanical connection. Physical mechanical connection, okay? Then we come along and we add the magic pixie shmoo. We soldered the legs, so now we have an electrical connection on top of a physical connection. It's just the way it needs to be. That's for a safety thing. I'm going to add a brass or copper strip that goes here, another copper strip that goes here. So our AC will come in on these two poles, this here, and our DC is going to come out here and come out here. Plate choke. Let's talk about my logic behind that for a second. The reason I wanted to get rid of the mag wire that was on the stock plate choke that was provided with this circuit is because in theory, on paper, technically these tiny little lines of mag wire would be technically enough to carry the amount of shmoo that we want to put in the RF deck. I'd rather just build one of my own. This is 16 gauge, yeah, 16 gauge or 18 gauge, 16. One of the two. Anyhow, mag wire, or not mag wire, but Teflon wire. This can put up with a ton of heat. This is porcelain on the inside that I cleaned, but it can put up with a ton of heat. The reason it needs to be able to put up with a ton of heat is because we're building ourselves a 4-tube out of an SB220 deck. There's another fan that we're going to put here blowing air across the tubes, and another fan that's blowing a lot of air circulation, but still we have to have something that can put up with heat. Each tube represents, well, a 2-tube I know off the top of my head is 1500 ohms, so roughly 3000 ohms worth of resistance to the circuit. So if we have a 2-tube, that drops to 1500. If we have a 4-tube, that circuit drops even further. Why do we need to discuss the operational resistive load of the tube in operation? We have to discuss that because it dictates the placement of this. This deck is nowhere near complete. I've still got to run some power wires here. I got to run in the AC. Bypass cap here, probably another one at the bottom of the plate choke. As you go down in your operational resistance, your inductor length to compensate for that on your tank coil from here to here is going to change dramatically. It's normally about 1 inch at like 6 turns, 7 turns. I'm going to have to fiddly fart around with it, but we're probably going to be at about 3 turns here. That's why you'll find that some Z boxes, they'll run out. It's not like you can just stack infinite amount of 3500Zs in an RF amplifier. The resistance gets too low. And eventually you run out of tank circuit. You can't take any more winds out of tank circuit. So what we want to do with our plate choke is it'll probably end up living somewhere in this department. Then I'll have a bypass cap right next to it. I want this thing to be able to make sure that it can't melt down. Another thing I have to add to this RF deck is I have to add a shield, aluminum shield, that sits between the base of the cabinet and blocks all the RF. The reason we have to do that is because this gives us direct access to the cathode. So on the top side of the tube you have the anode, on the bottom side you have the cathode. Okay? If those two somehow magically have a resonant pathway to each other, the top and the bottom of the tube, it can oscillate. The RF is going to go around in a circle. Where a filament transformer doesn't have horns on it, which are the caps that go over the end of the windings. It's a beautiful Peter Dahl transformer. Beautiful. But we have to provide a shield, one, to keep the transformer from having heat saturation from the fat-legged girl that's in here, the 3500Z. But two, the more important reason is to keep the RF that is going to be created in this little space from being able to saturate or couple or get absorbed to the transformer, and those are all appropriate terms. Normally in an Uber dork environment, we'd sit around and use the term coupling, keep it from coupling to the transformer, and us setting ourselves up for a repetitive cycle of oscillation. So the RF gets created, saturates the transformer, there in turn it leaks into the cathode of the tube, and the whole process starts doing this. Put a little shield here. It's probably going to sit somewhere right in there when we're done. But that's where we're at. I think what I'm going to do now is continue on with the power supply. So let me get this out of the way. Now what we got to do is mount up our plate transformer, get our on-off switches all set up. I've got one more board that I have to build, which is the metering board for the voltage circuit for the meter on the front of the power supply. Got to build the voltage board for the metering circuit on the front of the amplifier. Yeah, moving on. Next step, power supply. Okay, I think we're recording. Man, I wish this camera made a beep noise. I'm sure I got to get in there in the settings someplace and change it so it makes a beep. Well, I know I'm at least recording. Okay, so the transformer is now bolted down. Our filter cap is now bolted down. Our rectifier bridge is now in place. Our glitch resistor is now in place. Our bleeder circuit is now in place. So the magical high voltage pixies of a whopping 3,000 volts in this particular circuit, which is, as I'm sitting here building this, I'm thinking to myself, this is just so violently overkilled. It's just epic. This is epically overbuilt, by the way. These are like big boy parts, like we'd use on like a 10 or something. And that's just huge parts. But that's what this guy wants. So anyhow, pixies come from here. They go from our rectifying diode. Our ground is down at the bottom. Hot is at the top. So the hot lead or the ground lead comes out and it comes over here to our filter bank. Okay. Then our actual ground lead comes off this small piece of wire down here. It's going to go through a fuse. Anywho, committed, hooked up to our bleeder bank. So ground goes to bleeder. Our hot side comes off, comes out, comes across our filter bank, and then back out and across this 40 kVA wire and comes over to our glitch. The reason the glitch is so important is because it is what sits between the outside world and the power supply. If there's a short, whatever, this big old giant resistor is going to take up the huge electrical impulse that's going to be the short. And this allows us to have, I guess, an electrical way of expansion. This is what snubs that high voltage pulse of energy, and it protects our diodes. And in turn, when that pulse happens, it'll overload our fuse, which will be down here, and go pew. And then the bleeders come into play and will knock the high voltage offline. Also, when that happens, it'll knock out our contactors. So the ground for the contactors will go bink, and it'll come off. So the contactors will disengage, which will shut down our transformer. This is our bleeder resistor, and this is our time on timer down here. So we'll set this for like a second, maybe two. It'll be click, click, so you'll hear click and then click. And the reason we have to do that is because our filter bank is so big. I mean, when this thing is fully depleted to shmoo, the electron pixies, this actually looks like a short, like a hard short. So that resistor now in turn takes up the hard short value and allows the electrons to slowly start stacking inside the cap. I've explained this in I can't know how many videos, but it is what it is. So tomorrow, all I got to do is wire up on-off switch, wire up fuse, wire up the contactors, wire up the time-on circuit, and wire up the umbilical to go from here up to the RF deck, punch a hole in it for a fan here, punch a hole in it for a couple holes over in this area for a vent for exhaust air, because we want to blow some air in on these parts, especially these diodes. So we'll probably put the 120 millimeter, 110 volt fan here, and it'll in turn blow fresh air across these diodes. It's tumbled across it. And then we'll provide it a vent. Probably, well, it might come out the back. It'll probably come out the side over here. Over here in this area. That way we can get the air to wrap through the cabinet. So the transformer is not going to sit in there and cook, which should give this guy like a serious amount of key down time. This, believe it or not, is not rust. Of course, the little band straps, there's a little bit of rust on those, but this here, this is the varnish that's starting to peel up. This is a good transformer. This, I think, is going to a good project. So, on-off switches and fans, contactors, glitch. Probably be able to do this in about 2 or 3 hours, get this all finished up tomorrow. And then I can move on to the RF deck. So, I'll probably be 99% through the RF deck tomorrow. It's 2 a.m. It's 2:18 a.m. So, getting ready to shut down things out here. Time to go in the house. Gentlemen, we'll see you tomorrow. Click, click. Well, let's start here. Got our 2 fuse holders. Got our power wire lead. We've got our high voltage umbilical. And then we've got our umbilical that goes out to the RF deck. I made the lines incredibly, insanely long. So the guy on the other end, he'll be able to easily set this down on the ground and out of the way. I think the leads are like 6 or 7 feet. Silly long. Anyhow, glitch resistor is now in place. Our soft start circuit is all tied in. Our safety circuit with the fuse is all wired up. On-off action in play. Fan is installed. Transformer is partially bolted down. This took a lot longer than I thought it would. It's okay. So this power supplies, or the whole amp, everything is going to come in 4 boxes. Tubes separately, power supply separately, amp head separately, and then transformer separately. Now, as we can clearly see, we've got A, B, C, and D. When you get it on your end, you're going to have to bolt this thing down, this transformer. It's going to come with 4 bolts. And it's no harder than taking off the side, dropping in the transformer, and tightening down all 4 nuts. Then you're going to hook up the 4 wires. A to A, B to B, C to C, C to C, and D to D. You don't have to make these super tight. You make them too tight, you'll crack the porcelain. These you don't have to make too tight. This stuff you don't have to do anything with. This is already all tightened. All you got to do is drop in the transformer, tie on the 4 wires, peg them onto the transformer, and you're off to the races and running. Okay, now that I've spent most of my day working on this, the only thing I got left to do is now wire up the umbilical plug for the RF deck, which I think I'm going to do later tonight or tomorrow. And I think it's time for me to turn my attention to the RF cabinet. This looks really sexy on the inside. And I love the fact there's so much room to move around in here. I'm not going to lie. On most of these things I end up building, for some reason I do this to myself, I end up getting way too small of a cabinet. I kick myself in the boy bag every single time. This time, lots of space, everything's spread way out from each other. I'm not going to have to chase any weird glitches or shorts or anything. This is a super quiet 110 volt fan. We don't need to move a ton of air through here. We just needed to move enough to keep the bleeders from going into thermal meltdown and keep the diodes from going into thermal meltdowns. So, doesn't need much. Okay, let me pull the transformer out so I can take the power supply, put it down on the floor, and let's get the RF deck up here and let's get to work. What you say? I think I'm good to go. So here's the fun part. I just wired up the remote plug. And I'm standing here and I'm staring at stuff. I've got a bunch of 110 fans, and the filament transformer is wired 110. I'm not gonna lie, I did the whole portion of this port of the RF deck like so many months ago. I honestly don't remember what I wired, but I did just wire the plug for the power supply. I went ahead and I did the effort thinking that I needed 220 for the filament lead, brought 220 out here to the deck. I only need 110 and I don't need that much of it, so this is going to work out beautifully. I think what I'm going to do is I'm going to make this switch for on and off, and what on and off is going to do is just control the fans. That's it. It's got a operate standby key up switch here in the front. And as you can tell, we haven't done any of the input network yet. This is going to be on and off. This is going to be your filament right here. The logic behind that is that we can shut the filaments off, let the fans run for a couple minutes, cool everything off, then you can shut the deck off. This deck will run independently from the power switch on the high voltage supply. Power switch on the high voltage supply, all that does is run the high voltage supply. I know in a couple segments back I stated I wanted to have blah 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 in the power supply, and nah, I don't think we're gonna do that. On filament. Now the downside is, let's go get the face for this thing. Which I don't know if you guys have seen it yet. It's freaking gorgeous. Look at this. Oh, it's so pretty. So, final ignition. So the way base, high voltage, we're not going to use any of this. There's no point. And I think I'm only going to punch one hole in it. That's going to be for a high voltage meter, because to remote the grid and all that crap up here is just too much of a pain in the ass. So means I'm gonna have to have ugly ass stickers on the front of this thing. I'll even put a build number up here. I'll fill that in. I've put labels on this. Oh well. I'll set this aside. This guy at Space Age has been pretty cool. Space Age Graphics is the name of the guy's company here. Let's go over here and take a look at this. So the way I have this wired is ground comes all the way along all of these posts. Ground comes all the way along these base posts. It is quad wired redundant through the umbilical. Ground takes up far more pins than anything else. And my biggest fear with this, with a two-piece unit, I've made this very crystal clear in many videos, I hate making two-piece units. That's because if the ground comes away from this, the high voltage finds any other way it can to get back to this deck, and if that's through you, it will kill you. So we do have a ground nut. That's right here. And there's another one on the high voltage supply. Me personally strongly suggest that we utilize that with a piece of like number 6 gauge wire. Stupid overkill ground. You never can have enough ground, y'all. Just can't. So then these 3 pins and these 3 pins, sorry, and the focus on this thing kind of kicks ass, I think. These 3 pins here, these 3 pins here are 110 volts, and these 3 pins here, or these 3 pins here with an abandoned row in the middle, these 3 pins here and these 3 pins here are the other 110 volt. So technically we have 220 to the head. We do. But I think I need to get moving on this. So we'll go ahead and we'll solder a wire all the way across here. We'll hoop it back and we'll bring it to ground here. And then we'll grab some 110 volt and run it around. And come over here and tie this onto here. Or tie it onto here. I'm going to take another wire, take it back to ground. Yeah. Makes sense to me. How about you? And then I will take another lead and run it off over that way some way to run that fan. And then I can't remember if I showed this in the previous segment or not, me cleaning up this hole here with a punch. This is a mess, by the way. And this is flux. That's liquid flux. I wonder what else it leaked itself onto. Oh yeah, it's all over in this box. I don't know if you guys remember the transformer video where I was making input transformers. My liquid flux decided that it needed to go and drizzle its dizzle all over everything. Anyhow, I need to take another wire because this plate, this is like so. So we're going to have air going this-some way and this-some way to attempt to move enough air across all those tubes to keep them from going in a nuclear meltdown. But before I can even get that far, I got to build a shield. So let me move this out of the way. I'll come back and I'll clean that liquid flux off that aluminum here in a minute. Let's get, I'm going to bring my 110 volts up right here. Right there. Right there. And come right through here. Yeah. Yep, for the fans. Yep. Okay, I got a game plan. I'm going to do it now. Yay, let's go. Well, here's where we've made it so far. Doesn't look like a lot, but it's a lot. We've got our shield built to where we can grab this very burned up 3500Z, where we can stick that easily in the socket and have all kinds of clearance, as you guys can see. Good amount of space. All the wires that are behind this are high temp silicone or Teflon, which is also high temp wire. I flipped the fan around, added a guard on the back, so it makes a little bit more sense. Went ahead and put our Heiko connector on the back for our high voltage lead to go through. Then on the bottom, on the RF deck side of things, went ahead and we wired up our on-off switches. Our relay is now connected. We've got dual ground wires going for the case ground from here to the power supply. So dual redundant wire there. Just moseying right along. Got all our ground wires added. So now all I gotta do, back this back out. This would have been so much easier to do with just a regular aluminum cabinet versus trying to retrofit this SB220 cabinet. And we are so far from what we'd normally consider this to be an SB220. I never want to do one of these again. I did this simply to put a check mark on the bucket list. There's better uses for an SB220 cabinet in my opinion, but as we can see, we've got really good insulative space here. But there's really no way for RF to trickle its way in here and hit any of this, which is the most important parts of these horns. I had to add this plate here so that when we put the faceplate on, we have to have our third knob. Our third knob, which sits here. We have to have that so we can do our input tune. so we can do our input tune. So I need to have a little air variable that sits back here, and I need something to reinforce the backside of the faceplate. But we're close. We're going to start moving really quick now. It's the third person today that's decided, because I send them to voicemail, because I don't have my ringer on, they have to call back multiple times. Just kind of being jerks. People are jerks. God. Anyhow, we got to do the high voltage bypass. We've got to do our plate choke. And it needs to have a bypass cap at the base of it. Parasitic suppressors, input and output tune. Got a little ways to go. I have to modify this plate a little bit to hold a couple of these 250 puff 30 kV Drolorics, or doorknobs, not Drolorics, doorknobs. So one can sit like this, and the other one can sit like that. It's moving along. This took a lot more time than I thought it would, but that's okay. I'm on this project till I'm done with it, so it might end up being tomorrow, but I need to get the faceplate roughed on here, so it means I got to cut out the on-off switches holes in the vinyl, our transmit standby switch, our two tuner holes, and then I've got to mark the place for our third location, come drill that, get that mounted, get the tuners on the bottom side. Hopefully I got 4 good 3500Zs. The guy that actually owns this project has yet to send me the 4 3500Zs that go in this amp. And I think the customer's bucking to get 4 brand new tubes. So we'll see how this works out. I don't know. We'll see how this works out. All right, I better go return that phone call. We'll be back. Well, I think this is the portion of the video that everybody actually watches, the main portion of the end of year video, where people actually want to see what I got done this year, which was not much. I save these every year, and these are the used flats of HG transistors that I have used just this year alone. I will pitch these at the end of this video segment, thank God, and I get all this shelf space back. This is either what has come through here for me to build with, or that I have sold, or whatever. I don't really want to get into the market of selling transistors, but that's a lot. Each one of these represents 20 transistors, so 20, 40, 60, 80, 100, so on and so on and so on and so on. That's a lot of god dang transistors in my opinion. But that's on par for what I about normally do. I mean, I try to stay busy over here, don't get me wrong. And I am so grateful that you guys continue to want to work with me, and you guys are patient to wait for me to be able to work on your projects. Here are the, and it's so bad, you guys, when I was pulling this off the shelf, there was literally transistors falling out of the, I found 2 or 3 extra transistors I didn't even know I had. Here are the 454 transistors that I used. I've gotten to use a lot of those. I really want to get around to making more boxes of those. They run great. They're a good component. So as my friends from Colorado can attest that were here just last week, as I go and I change out pills, I throw them in that bag. Well, this bag is full. Completely full. This is what I filled up from 2021 to now. And it being 2023, I'll set this aside. So this is about the third 1 gallon bag that I've filled up with transistors over here. Those are all bad. Tested, confirmed bad. As tempting as it is, I have dreams about torturing somebody sometime. Like, somebody has done me wrong, right? And I get all these bags of dead transistors I got. And I dump them in a pile, and I throw one good transistor in at the bottom and tell them they've got to sit there and test each one of them by hand until they find the one that's good. I think that would be hilarious. Now, when I die and I go to hell, that's probably what I'm going to end up having to do. That's going to be my torture by Satan. But at the end of the day, this bag is done. I'm going to throw it up on the shelf with the other ones. And I have nightmares thinking about, these are full of beryllium oxide. How much the government actually lets you store in whatever form. Because there's a rule. There's always a frickin' rule, right? Needless to say, this year has been productive. And I have been very blessed with your guys' love. And I want to say thank you for supporting me, as always, and letting me be able to work on your guys' projects. And really, thank you for the patience. Like, this guy here has been waiting forever for me to do this project. The reason I didn't want to do this particular project, and I'm not going to lie, I put it right out on Front Street, is that somebody else has already attempted this with this cabinet. He bought this cabinet used, and now I have to go back and redo their work, then plus add my specialness on top of it, and then try and work within the constraints like where they'd place their transformer and where the fans were placed and those kinds of things. Those aren't things that I get to go redo. I have to come along and I have to make them cleaned up and better and then redo it myself. So not fun to me, but this project has taken like 4 more days than I thought it would, but then again, everything takes longer than I think it would. I don't know why why I don't go ahead and readjust my perspective on things, but I used to bring out here all the shipping receipts. Well, as I said last year, we went paperless, thank God, because that used to take up a ton of room too. And it cost a lot, from the ink to the paper to it was a pain in the ass. So now I print the label, I email it to the UPS store and let them use their ink and their paper. This has been good. It's been a good year. As far as business goes. As far as personal life and family and people dying, it has been horrible. The last 4 months have just been horrible. I swear to God, I'm losing 4 or 5 friends a month. And it starts to weigh on a guy after a while, especially when you start to lose big ones. We just here last week laid to rest my friend brain damage, and that's the reason that we're here so late into the new year already, and I'm still working on this. So I just want to say thank you guys. I appreciate every single one of you, honestly. And let's just mosey on. I get all this shelf space back. Yay, I can put a 16 pill in this place. Okay, let's go. Let's get on to the next bit. Well, I think that I'm about ready to run this thing. I'll go down the checklist of a couple things. Oh, I know what I got to do yet. Not ready to run, but close. I got to do a meter. Got to have a voltmeter on it at a minimum. I added this extra strain of wire. I might actually end up deleting that. Depends on if I want to put a light, like a 110 volt light, inside the voltmeter. I was able to scrounge around. I got 2 used iMacs over here, but they're both at 100%. These are my bench tubes. These two RF parts tubes, which I'm getting ready to replace. That's probably going to be one of the next few videos I get to go shoot. I'm really excited about that, and I can't really talk about that yet. It's not quite at that stage, but we're getting close. Tank coil is in, the RF inductor circuit's in, all the parasitics are in, the tubes are in, plate choke is tied in, RF shield is in, our input tune is installed on the bottom side, and the sides are installed. All the fans are hooked up. On the bottom side, our input network is now in place. This is it, our input network. Simple pi-L circuit, tuner, coil, tuner. And then we use the tuner in the front to complement the final tuner. And that's what allows us to be able to take and change our input resonance specifically. You know, let's say I want to dial it in for channel 1. I have the option for channel 1, then I specifically dial it in for channel 2. The whole idea behind this is to make this amplifier as clean as possible. And it's the beauty with the tube amps is that we can do that and we can make it pinpoint precise. When we look at it on a chart, which you guys have all seen me do many times, you get your frequency dip, the frequency that it's resonant at, and then up. And the tighter we can make that input Q, the narrower we can make the input Q, the less chance we have of having RF pass through this device and get amplified that isn't within the specific frequency that we're wanting to rectify. If I made it so that the input Q is like, let's say here's channel 1 and here's channel 40, and I made it so that the input Q is like this wide, any spurious RF that isn't on the frequency that you're wanting to talk on is going to get rectified, and it could be all over the place. Where if we make the Q tight enough on the output tune and tight enough on the input tune, it's almost impossible. But I think we're ready to run it. I want to spend a couple more minutes looking at it, but I will put the power supply all the way together, as in I want to put the power plug on it, and I want to put the transformer back in it, because I took the transformer out so I could move the RF deck around and not have to worry about bending anything. Yep, I want to put the transformer on it, and I want to, oh, I got one more thing I want to do to the power supply. Let's jump over to that real quick, and then we'll zip back over here. So this is the bottom side of the amp. And what we're wanting to do is to make it so that if the transformer does hum a little bit, or one of the contactors does hum a little bit, that it's not directly bolted to a snare drum. So we're going to add some kill mat to the bottom of this thing, which all it really does is add density. It's a piece of butyl material with aluminum foil on top of it as a backer. Some of you guys from the 80s and 90s that played with stereos will be familiar with this stuff as hush mat. Well, hush mat is butyl with aluminum on it. Well, their patents on that have long since run out. So I use the kill mat. It's a little bit thinner, but it achieves the same goal, which is to simply add mass, which slows down vibration noise through the metal. So makes it more dense. And I said, like, the goal is the transformer obviously sits here on these 4 mounting posts. The idea is when my friend gets this on his end and he goes to turn it on, he's not listening to clunk, you know. It'll be nice and quiet for him. And the more noise we can kill on the floor of this thing, the quieter this thing's going to run. Not that I'm saying that the power supply hums, because the last time I powered it up, it did not hum. Did not hum at all. The contactors, when they engage, they're going to go clunk clunk, and I want to deaden that noise up, hello, as much as possible. So let's throw one more piece on here. Never going to have too much. Never have too much. Let's put that in there. And once I get this on, I can screw the base of the power supply on. Okay. All right, I'm going to put the base on it. And then I'm going to put the power supply on it, or the transformer in it, I mean. And let's test the high voltage supply. It might work, it might blow up. We don't know. We'll see together. You, me, and everybody else. Okay, so a couple little problems. Start here. So soft start is now working on the high voltage supply. That was not, had one wire backwards on the timer, so it was working as a time on, or time off, not time on. So I got that figured out. Now let's jump over here to the RF deck. Okay, so now here we are overlooking at the RF deck. And so first I lit the RF deck. Got my fans running. Then I go to turn the filaments on. And what I had was 2.5 volts on our filament leads. And I'm like, that's messed up. So I thought, okay, maybe that they had wired the transformer wrong, which I'm not gonna lie, every single time I thought I had something figured out that was just like fixed in stone with this box, the people that wired this before me have not done me any justice. Okay? Everything that was in here was wired wrong, is the best way to put it. So when I go and I wire it for 220 on the primary side, which I think are the two primary leads, and what ends up happening is I got my 5.5 volts, but then the transformer got really silly hot. Like, I could smell it, and I was like, oh, stop. Because without this transformer working, I got big problems, right? This whole project comes to a screeching stop until I can find another 5 volt, 60 amp transformer. So I started thinking, well, maybe they got the primaries and the secondaries going, or backwards. So I took all this wiring apart, which is the secondary on the transformer, and well, here. If I drop one of this is apparently a hot 110 volt lead, and this is a hot 110 volt lead, and they had them tied together. Well, the transformer is actually 220, or pardon me, 110. So now I got my 5.5 volts for my filament, which is great. The other thing I noticed is that my auxiliary secondary tap that runs the relay and the bias circuit and all of that stuff was way low in voltage. It's like 43 volts. I'm like, wow, something's seriously wrong. So I pulled one leg of the secondary off so I could test it, and now that I've gone to a single grounded source, now I've got my 97 volts. So once I rectify that into DC through these two bridges, which there's something wrong here, I'm going to change that out to a different diode. Once I get that rectified, that'll get me my 125 volts, which means I'll get my relay, and then I can get bias flop. Everything has been wired wrong. I could not even take the wiring of the filament correctly. But now I have the right voltage, and I have the right current draw for the filaments on the tubes, and the filament transformer is just sitting here at temp at 86 degrees. So let's take all this apart, and actually I set it up so I could shut the filaments off, let the tubes cool off. Let's neaten all this up and get it all zip tied and buttoned up, because I think I finally got this figured out. And then I got to change these diodes here. I don't like this circuit whatsoever. Well, here we are, attempt number 7. I've had shorted tubes. The zener that came with this thing for the bias is shorted. It's just been really tired of working on this thing. It's would have been easier to say to me, hey, BBI, you want to build it from scratch? Would have been easier, a lot easier. Okay, so I got my filament volts, 5.4 volts, filament off, filament on. Okay, let's grab this little tab, we'll click it on case ground, we'll go over here to DC. We have our 132 volts cutoff, which means now our relay is powered. This section thing is, this power supply, I've blown it up like 3 times, just working through all the problems. The shorted tube was this thing looks good from the outside, but the filament and grids are shorted out on this tube. So these 2 pins to these 3 pins are all shorted internally on the tube. This is bad. So now when I step on the pedal, beautiful thing happens. The relay works. I created a new bias board for us. And you're right down there to operate. Then back to cutoff. Back to cutoff. So I think I'm ready to put the plate transformer in the power supply now. We'll hook up our high voltage wire. I think I'm ready to run this now, finally. 6.5, 5 hours later. This didn't take 5 hours to figure out, just to get to this point where I've tested everything and I feel very comfortable with it now. It has taken this long. Transformer's not overheating. I am grateful. Okay, let's drop in the plate transformer and let's get some high voltage in play here. Okay, so what you're looking at here is the 1000-to-1 reduction probe, grounded to the cabinet of the head unit, amp deck, and I'm probed on the end of the wire. Now what we're looking for is for when this thing to turn on, slowly ramp up to 2,000, 3,000 volts, and within about 10 seconds the soft start fully engaged and we have full power supply. So here we go, ready? 2,000, 3,000, 4,300. That's with no load. So that proves to me that the high voltage circuit is working. The soft start is working, although it took quite a bit of little tweaking to get it just the way I want it. Now we got to wait for this thing to bleed all the way back down to 0. And we'll go ahead and we'll hook it up to the bypass cap on the inside of the RF deck here. And then we'll turn on and run it and see if we've got any high voltage leaking. That's without the filaments on, of course. And then we're going to run it with the filaments on and the high voltage on and see what we got for 0 signal. So we'll let the bleeders do the bleeding thing and we'll be back. Okay. So now what we're going to do is we've got our 1001 reduction probe. And right here is our high voltage meter. Let's see what happens now. 2,000, 3,000, 4,000. No high voltage leak. None. Which is great. Freaking great. Okay, so now we'll kill the high voltage power supply. We'll turn on our fans. And we're going to bring on our tubes. The filaments are lit. Step on the pedal. Now I need to flip it over and we'll do bias flop, but this should have dropped a lot quicker than this. So let's not have good connection with my center tap. All right, time to start fiddly farting with it. Away we go. Okay, going from left to right. This is our cutoff voltage. That'd be right to left. Let's go left to right like I said. Plate voltage, 4,300 volts under float. This is the amount of current draw from our filament, or pardon me, our bias circuit. This is our cutoff voltage from our power supply. Step on the pedal, pulling approximately half an amp. Our float voltage drops down to 4,000 volts. Let's come off the key again. Everything hops right back up, goes back to 0. Let's step on this here. Our cutoff voltage drops to 5.5, which is good. It's about what we're shooting for. So, right now, technically, we can make RF with this thing. So a little bit more twiddly farting around with it. We're good to go. So that's about, let's see, 600 mils. That's total in the power supply, divided by 4. 150 mils per tube. Works out to be just about spot on. So the tubes are in hard class AB. Now we'll go ahead, we'll pull the high voltage off. Here's our float voltage. Now watch this. Whoop. Drops it right down the way it should. We can also see our cutoff voltage react accordingly to plate voltage. Now we're already down to 22 volts. 0 volts, just like that. Power supply back up. So we'll shut our power supply off again, and we'll see how slowly it takes for it to bleed off. It's because the tubes aren't reacting with the supply. We'll go ahead, we'll step on the pedal. Yep. We're in the state of Shangri-La now. I'm excited. If I want to increase bias, I can go over a couple diodes, but this is where I know the tubes are going to be the happiest. That's good. Let's pull everything off this, and I want to hook some coaxes up to this, and let's see what happens. Kind of interested to see what happens now. So I went ahead and modify the diode board for the bias. Got our 4,300 volts on the plate. Hello. I gotta get a different amp clamp ring. Anyhow, there we are. About 400 mils, but we're up to 8 volts on the bias circuit now. And the reason we did that is because the tubes, as soon as I'd step on the pedal, they were flaring and running away. Let me reset. I'll show you how stable this is now. Okay, so what I was talking about, we're going to look at those back 2 tubes because it's going to show up more prevalent on the back 2 tubes. Is how quickly the tubes will flare. Well, what we're looking for is when I key it down, you'll start to see the tubes are starting to get a little bit orange. What we're looking for is for them to flare and come up partial in temperature, but them not run away and get silly hot. They're just at idle right now. They're not getting silly cherry red. Now these other 2 tubes on the left, the bells are starting to come up on them. So like I said, once we step on the pedal, what we're looking for is just the bottom 2 bells to kind of warm up a little bit. We'll see the back tubes kind of come up. And now these 2 tubes on the left, you see how they're coming up just a little bit red? That's what we're looking for. We're not looking for anything more aggressive than that. So I had to add a little bit more bias to it to get it to come to full cutoff, or to full operation, so it won't run away. And then I come off the pedal, and everything instantly cools down again. Okay, I'm kind of interested to see if this thing even works at this point. A lot of work gone into seeing if, just to power and light these things. So let's see what happens next. Let's get some coaxes hooked up to it and put a few watts of drive into it. Man, all I'm gonna say is this thing is friggin' awesome. Let's get in here a little bit closer. So what we got going on is that end meter there is in the 1x position at the moment. So we've got the bench 2950 at 1, 2, going into the bench 2 pill. So let's go over here and we'll drop that thing down into 5x. Step on a pedal. 1, 2. It's making over 5,000 watts plus. It's actually just barely kissing the end of the stop peg. It's just like here. 1, 2, and well over 1,000 bird. Now when we come over here and we look at the tubes, how they're operating, they're not getting excited at all. All right. 1, 2, 1, 2, 1, 2. 1, 2, 1, 2. Off the foot pedal. Anytime autofocus, it's like it's set for slow or something all of a sudden. 1, 2. 1, 2. It's getting right up there. And I mean, it's getting with it. I'm super excited about this. I'm not gonna lie, I'm kind of digging this. I'm gonna keep playing with it. Hold on a second. This is actually gonna be kind of fun. Been a lot of pain in the ass. The input tune on this thing is flat as a coffin nail here. I'll show that to you in a few minutes. But, a little bit less than 400 watts drive. On that stop peg in peak mode. Bing! Now I can drive it harder than this and I can get more power out of it. The problem is I keep blowing the 30 amp breaker that's in the back of the box, which is good. That'll protect my guy and it'll help him save his tubes. I was figuring this thing would do around 5,000 watts, taking into account you can push each tube to about a little bit over 100 or 1,000 on like a really hot power supply, because that's what we've got attached. About 12 to 1,300 watts and safely do it, and the tube kind of stay together with the right kind of bias. Well, we got the right kind of bias on it, so here, I'll push it out to its max. Put about 450 into it. Nope, pop the breaker. Oh, I love it. I love it. Okay. So we've gone ahead and we've switched over to the Striker 955. We're on the 2x scale right now, you guys. So full meter movement at about 125 watts a drive. At about 1900 with 125 watts a drive out of 4 tubes. It's not too bad. At 1, 2, 1, 2, 1, 2. But the part that I like is this here. The notoriously hard to work with and get around 955 inputs meter. Check this out. 1, 2, 1, 2, 1, 2. Zero reflect. And let's see something really cool. Let's go up here and let's take a look at so used to working with the other camera. Let's go look at this 5 watt slug in reverse. 1, 2, 1, 2, 1, 2. Squeaky clean input. I mean, 1, 2, 1, 2. That's our pass through. 1, 2, 1, 2. That's going into the amp. Let me back this up. Drop this down a little bit. So now you can see both of them. They're both relatively in focus. 1, 2, 1, 2. All right. Now, without breaking away and flipping any more switches or anything on the sidelines, let's bring this around. Let's take a quick look at the spectrum analyzer so we can convince everybody there in YouTube Gargler land, oh, it's another splatter box. No, no, it's not what we do here. Radio, amplifier. 1 1 1 1 1 1 1 1 0. It's clean. It's like a virgin. Hello, 1 2 1 2. That's with 125 watts of drive, y'all. Hello, 1 2 1 2. Just cruises there. Let's go over to lower sideband. Hello, 1 2 1 2. Hello, 1 2 1 2. Hello, 1 2 1 2. Then them suckers glow. Let's go back to the break and pop into the breaker thing. That is not what we want to do. We don't want to have that happen. That's very hard on everything when we do that. The fans quit, power supply has an issue, everything goes, ah, and then quits. Not cool. Not cool at all. So, let's just say that maybe I bypassed the fuse at some point. This is what we're running off of, is a little 30 amp glass fuse, and we did that intentionally, kind of short fused it a little bit. Bypassed it with some aluminum foil. And this thing makes about 5,600 watts. With about 450 watts of drive. Which is cool, in my opinion. But that's murder in the tubes, in my opinion. So, you got a couple $1,000 box with $1,000 worth of tubes in it, and then you're going to go and overdrive the bejesus out of it. Hey man, it's your amp. You do with it what you want. But I'd strongly suggest keeping the drive under 400 watts. It's going to be the best on the power supply, best on the tubes, best on everything here in this picture. I'm telling you that this amp has been a ball sack buster. So you can't tell it right now, but I painted these knobs. Very, very carefully painted these knobs. I taped off everything, taped off the edges, went and I scuffed all the plastic up, and I taped these knobs so they're black to match the face. Every single one of these knobs was missing its journals, the little set nuts that allow them to be held in place. I'm like, no big deal. Another 20 minutes, so I go over and I cut some screws and I cut some slots in them and I make some set screws to fit inside the journals. Set screws are missing. I go to put the one on for the input tune. Not only is it missing the set screws, it's missing the insert. I got lots of SP220 knobs because this is my thing. This is my jam, man. I got SP220 parts. I gotta go. Every single part that was supplied by the original customer was wired wrong or missing some kind of parts or wasn't right in some way. I mean, even when they grounded the grids on the bottom of the tube sockets, they didn't even bother to tighten up the nuts to hold the grid screws in place. It's all good. Shut the filament off. Shut the high voltage off. You know what? Bring the filament back up for a second. Bleed off the high voltage supply. We're doing this all in the blind. The reason we're doing this in the blind is I don't have any meters built for it yet. Nah. Once again, I took the time and I taped off the meter faces and did everything upright and made them black. Done. Okay. High voltage is bled off. Let's let that cool off for a second. Now I want to hook the 2-pill back up, and I got to do the abuse test to it. I've got to run it. throw like 1,000 watt, 2,000 watt, 3,000 watt carrier with it. I got to see where it maxes out. So hold on. We'll get that set up next. Okay, so 1, 2, a little bit too much. 1, 2. Okay. So I'll put that down in 5x. 1, 2. 1, 2. Focus up anytime, camera. So I spent all the money on you is for to give you a quick focus, not this BS. 1, 2. All right. This test is to do a heavy high carrier into max peak power. So we're going to vary our dead key from about 10 watts up to 200. There's 3,500 carrier. I'll call that a win. Bring this down about a kilowatt. I'll dig that. 1, 2. 1, 2. It's working just the way it should. Played with the knobs too much. All right, let's retune it. Son of a gun. Okay, we have every fuse bypassed, every safety thing that I've got built into this thing, short fusing it and whatnot, bypassed. Putting 550 watts into it. 1, 2. That's our drive. That first big hash mark there. Get out my laser pointer. That first big hash mark right there is 500 watts. So, taking the 955, driving it into the 2-pill, driving it into this thing. Do not operate it like this, please. Hold steady on the stop peg. Just blink, just bling. Ran it to the corner on both scales, RMS and peak. So let's go ahead and kill the high voltage off one more time. Step on a pedal. Key the mic real quick. Just come over here. We're gonna get our it's our 5 kW slug. I'll pull the 1,000 watt element out. Put 5 kW of that right there. Okay, so now the 10 is 1,000, the 20 is 2, and the 3 is 3,000, and so on and so on. Re-engage the depth voltage. Hello. Hello. So well over 2,000 bird and 5,000 plus peak power. Probably gonna murder my little 2-pill here, but let's put it up on sideband. 4,000 watts average. 4,500 watts average. But look at the tubes. You guys will get a kick out of this. It's like a light show. Ready? Here we go. All right, so it's capable of 4,000 plus bird easily. and over 5,000 watts peak. Easily. I love my job. Hello, 1, 2, 1, 2, 1, 2. Hello, 1, 2, 1, 2. You know, the one thing that hasn't given me a hiccup yet at all has been the power supply or the soft start circuit. So click on go. So shut that down. Step on our foot pedal to help bleed off the high voltage. All right. We're gonna shut our filaments off. We're gonna let our fans run for a couple minutes, strip some of the several hundred degrees worth of heat that are going on inside this box off. Now I gotta put some meters on it. I mean, honestly, I gotta do some shit. And we gotta get the faceplate on there. So I've gotta create a downsizer for my knob. Hopefully find some extra set screws, or make some. I guess I'll have to make some more. Man, this has been a lot of work. All right, let's get the faceplate on. Let's get our high voltage meter mounted up here. So we don't really care about amps. No one cares about amps in this situation. And yeah, let's get this done. I want to be done. I don't know about you guys. It's time to be done. Okay, one more quick little test before we go and we strip all this apart. We've got to look at our plate voltage under load. So right now we're idling at 4,300 volts. 4,000 volts. Hello. 3,300 volts, 3,400 volts, full chooch. It's 5,000 plus. Hello. Hello. That's just beating the hell out of this meter over here. Hello, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Okay. Hello. 3,400 under load. It's really important. That'll come into play when we go to set our meters up here in a few minutes. So, okay. Well, gentlemen, here we are at the end of the story. I am really glad to be done with this one. No lie. This took a lot of work. A lot of work. Now, I built a custom metering board. And I know this is supposed to read 4,300, but it's actually on the stop peg. I go any further than that, it's just going to burn it up. So there's no point. The foot pedal key up is on, down is off. And of course the sequence of events is turn this on, then turn on the high voltage. So I'm done. This master creation is completed. We've shown it make over 5,500 watts and over 4,000 watts average out of a 4-tuber. Power supply is built like a tank. And what can I say? It all came together. A lot of broken stuff, a lot of worn out stuff. Thank God I had all these parts over here sitting here to be able to fill in the holes. Just shut off the high voltage. Big thanks to Siglant, big thanks to MacMan, big thanks to XS Power. Big thanks to my Patreon that stepped up and said he really wanted this thing and that I needed to hurry up and get it finished. Big thanks to the customer that sent it up here saying, hey, I want you to build this out. Gentlemen, I'm tired. I got nothing more I want to give this thing. Filaments off. On that note, I say thank you. I cannot wait to see what 2023 is going to bring. God knows I've got enough projects coming up to gag a maggot. I can't apologize to you guys enough about the delay on the video, but we got it done. On that note, gentlemen, I say I appreciate you. We'll see you in 2023. Click click, click.